Greetings, AP Chemistry students. This is Mr. Harper with the third episode of your basic training podcast series from the summer. And today what we're going to be doing is venturing into Chapter 3 and talking about some of the topics that you will find therein, specifically about composition and empirical molecular formulas. During this podcast, I'm going to show you guys how to do probably the most difficult kind of calculation you're going to encounter in Chapter 3, which is the determination of empirical and molecular formulas from data that you will be given in those problems. And we're also going to review a little bit from things we talked about before and do some general stoichiometry here at the end of the podcast as well. This may be the last one that you have to watch here during the summer. I am going to have a review podcast I've put together here somewhere towards, middle of July or so. And there's going to be one more that I will have you guys watch also probably on significant figures and accuracy and precision, things like that you will encounter in the summer reading if you have not done so already. So let's go ahead and get started. Okay. So if we look here at the title of, the subtitle, I suppose, here of our podcast, what we're talking about is composition, empirical, molecular formulas. There's different ways that you can express the composition and the makeup of a chemical substance, okay? And this all goes back to a law you guys learned last year called the law of constant composition, which says that any sample of a pure compound always consists of the same elements, okay, combined in the same proportion by mass, okay? So in other words, you could also say this mathematically as the percent composition of a given compound is always the same, okay? So say, for example, if we consider this turkey right here, which is called cyclopropane, okay? No matter where I find this substance on Earth, whether it's in the United States or China or India or where have you, it's always going to have the same makeup, okay? And that makeup can be expressed in different ways, okay? Here are the different ways that we can write this, okay? This is, as you guys will recall, called a Lewis structure, or sometimes called a structural formula, okay? If we look at this Lewis structure for cyclopropane, we're going to see that we have 1, 2, 3 carbons, and if we count them, 1, 2, 3, 4, 5, 6 hydrogens, okay? One molecule of cyclopropane contains 3 carbons and 6 hydrogens, so we could write the molecular formula like this. It is C3H6. That tells me that in one molecule of cyclopropane, there's 3 carbons and 6 hydrogens, okay? Now, back to the name of this turkey. This is a little bit different from what we talked about the other day. We talked about how to name binary non-metal compounds, okay? When we're dealing with organic molecules, which are ones which are made just out of carbon and out of hydrogen, there's other naming rules that apply. This baby here is called a propane, okay, because it is an alkane. It has all single bonds, you guys will recall from last year, and there are 3 carbons, okay, that makes it a propane, and it's a cyclopropane because all of these carbons are attached in a ring kind of shape, okay, they're not arranged out in a line, okay, so just a throwback from last year there, okay, so this is C3H6, the molecular formula, okay. Now, that's probably the most common way that a chemist will express the makeup of this compound. But sometimes, we also might express this in terms of percent composition. I might say, by mass, what is the percent carbon and what is the percent hydrogen in this compound, okay? Now, here's how we would do that. First of all, let's look at what the total molar mass of this compound is, okay? The molar mass we can get just from the formula. There's 3 carbons, okay? Each carbon has a mass of 12.01 grams per mole approximately. Each hydrogen is about 1.01 grams per mole. So altogether, roughly, this is a molar mass of 42.0 something, 08 or so grams per mole. Something of that nature, okay? That's the molar mass of this compound, okay? Now, if I wanted to determine what percent carbon it was, I would simply take the mass of carbon found in 1 mole of this compound, okay? So if we have 3 carbons, if we have 1 mole of this compound, okay, 3 carbons is going to be 36.03 grams, okay, divided by the total molar mass of the compound, which ends up being 42.08 grams per mole, okay? If I go through here and do the division and multiply here by 100%, I'm going to find that this turkey is going to be 85.6% carbon by mass, and analogously, I can also determine that it is going to be 14.4% hydrogen by mass, okay? And through just the same mathematical process, okay? Here's another way that we can express the composition of the substance, okay, in terms of percent by mass. A third way that we can describe the composition of cyclopropane is using something called an empirical formula. Now, what an empirical formula does, which is different, okay, than a molecular formula, is the empirical formula shows you the ratio of the elements, okay? If we look here at the molecular formula compound, it's easy to see that there are there's six hydrogens and 3 carbons. We could reduce that formula to make it look like this: CH2. Okay, so I just divide this by divide this and simplify it, I get CH2. Now, this does not say that a molecule of cyclopropane contains only 1 carbon and 2 hydrogens, but what it tells me is that the ratio of hydrogen to carbon is 2 to 1, or you could also say 1 carbon to 2 hydrogens. There's the difference between empirical and molecular formula. Okay. Now, again, if we just kind of consider this example, or consider the same distinction between empirical and molecular formulas for these 4 compounds. Okay. For cyclopropane, we already said that I'm just going to call molecular formula, I'll abbreviate this MF, okay, not something vulgar, but molecular formula. We already said for cyclopropane is C3H6. The empirical formula, we said the lowest reducible terms, the lowest ratio of carbon and hydrogen here is going to be 1 carbon to 2 hydrogens. CH2 is the empirical formula. If I do the same thing here for this next molecule, this, guys, by the way, is called cyclobutane. Okay, it is a cyclo because, again, all the carbons are attached to each other, and it's a butane because we have 4 carbons now in the compound. Okay, the molecular formula here, if we count it up, we've got 1, 2, 3, 4 carbons, and then 8 hydrogens. So this is going to be C4H8. Okay, but if we look at the empirical formula of this compound, again, we're going to see that the ratio is there's 1 carbon for every 2 hydrogens that are in the compound, okay? Here if we look here at this next one right here, this we would call ethene, you could call it, okay? Would be the name of this compound right here. If we look at the molecular formula, okay, and we count it up, there are 2 carbons, and there are 1, 2, 3, 4 hydrogens in the compound. So this is going to be C2H4 is the molecular formula. The empirical formula, in the same logic as we applied before, is going to be, again, CH2. Now, if we compare these 3 compounds, guys, here's the point I'm trying to make, okay? The empirical formulas, if we look at these compounds, are all the same, okay? What that tells us is that the ratio, in each case, of carbon to hydrogen in each of these compounds is the same. That tells us the ratio is the same. But notice, the empirical, or the molecular formulas, rather, of cyclopropane, cyclobutane, and ethene are all different, okay? So different molecules can have different molecular formulas, but can have the same empirical formula. They don't have to, but it can happen that way. Okay. Now that you guys have an understanding of what the difference between an empirical and molecular formula is, what I want to demonstrate for you and walk you through and have you do with me is some of the more difficult calculations out of Chapter 3, which is in determining empirical formulas and molecular formulas of compounds from data that you're going to be given, okay? So you should have some paper out and a calculator and a pencil and do these problems with me. And then I'd recommend that after you watch me do them, you go through and do the assignments out of your book, okay? So here we go. These are actually some problems off of your assignment from Chapter 3. So this is going to be problem number 59 first, okay? It says acetylene. Okay, now acetylene, by the way, guys, is a compound that is used in welding. For all you guys that are going to take metal shop or do something in the construction academy, oxyacetylene torches are what you use for gas welding a lot of the time. Okay, acetylene is a colorless gas that is used as a fuel in welding torches, among other things. It is 92.26% carbon and 7.74% hydrogen by mass. Its molar mass, we know from a separate experiment, is 26.02 grams per mole. And what we're going to do here is we're going to calculate the empirical and molecular formulas of the compound from this data. Okay. Now, to solve this sort of problem, guys, there's a series of things we're going to do. Okay. The first thing we are going to do is we are going to make an assumption. Okay, the second thing we're going to do is we're going to convert some numbers to moles. And you'll see why it's important here in just a second. Okay, step 3, what we're going to do is we're going to find a mole ratio. Okay, and this is going to give us, when we do that, the empirical formula of the compound. And then lastly, step 4 is we're going to find the molecular formula. I'll just abbreviate that MF for molecular formula. Okay, there we go. So that's how we're going to solve problems of this type. Let me go through and walk you through this example. That'll make more sense. Okay, so here we go. We know the compound is 92.26% carbon and 7.74% hydrogen by mass. Okay. What we're going to do here is we're going to make these numbers useful, we're going to assume that we have a certain sample size. Okay, what I like to do is I like to assume that we are working with 100 grams of the compound. Okay, so we have that much of the compound. Now what that means is that if we have 100 grams of the compound and by mass it is 92.26% carbon, that means we have 92.26 grams of carbon in that sample, and by a similar piece of logic, we are going to have 7.74 grams of hydrogen in the sample. Okay, we made our assumption just now. I know now a mass of carbon and a mass of hydrogen that I have in that theoretical sample. I'm going to now convert these masses into moles. Okay, so we're going to use our molar mass of carbon. Okay, 1 mole of carbon has a mass of 12.01 grams. If I do the conversion, okay, we get 7.68 moles of carbon. Okay, in a similar fashion, I'll do the same thing for the hydrogen. 1 mole of hydrogen has a mass of 1.008 grams or so. Okay, if I do the math here, I get 7.68 moles of hydrogen are also present in this sample here that we assumed we have that certain sample size. Okay, now the next thing I'm going to do here is I want to find a ratio, because when we're finding an empirical formula, guys, what that's going to tell us is the ratio of one thing to another. Okay, so what I'm going to find is I want to know what is the ratio of carbon to hydrogen. Okay, what I'm going to do here is I'm going to take the moles of carbon and divide by the moles of hydrogen. Okay, so 7.68 moles of carbon divided by 7.68 moles of hydrogen. Okay, now if we simplify this ratio, okay, right here, 7.68 divided by 7.68 is just 1. Or I could also say 1 mole of carbon for every 1 mole of hydrogen in the compound. Okay, what that tells me, guys, is that my empirical formula of acetylene is just CH, okay? Because there's 1 mole of carbon for every 1 mole of hydrogen in the compound. So there we go. That's the empirical formula of acetylene, okay? Now, again, that just tells us the ratio. That does not tell us what 1 molecule of acetylene consists of, okay? So the next step now is I'm going to find my molecular formula, okay? To do that, we're going to use another piece of information that we're given. We're told the molar mass of acetylene is 26.02 grams per mole. Okay, if I look at my empirical formula here, the molar mass, okay, of this empirical formula is like roughly 13.02 grams per mole. Okay, this is the lowest ratio of carbon to hydrogen in the compound. To change that now into the molecular formula, I'm going to have to multiply that by a number. Okay, to get the number I have to multiply by, I'm going to divide the molar mass, okay, by the molar mass of the empirical formula. 13.02, guys, goes into 26.02 about twice. Okay, so if I just do that, divide by molar mass 26.02 divided by 13.02, this is about 2. So what that tells me is I'm going to multiply my empirical formula by 2, and the molecular formula of the compound is going to be C2H2. And there we go. That is the molecular formula of acetylene. And that's how you do it. Let's look at another example, okay? This is a problem number 61 off of your assignment. And actually what I'd recommend, guys, is that you pause the podcast and do this problem on your own first, using what we just did. Go through the process, make the assumption, and then do the math. Do that on your own first, and then come back and watch me do it. Okay? That's what I recommend you do. So if you want to do that, pause that now, and then come back and watch the answer. But here we go. Okay, what it says here in problem 61 is that nitrogen and oxygen form an extensive series of oxides with the general formula NXOY, okay, where those X and the Y are subscripts. They tell me how many nitrogen, how many oxygens there are in the compound, okay? One of them, it says, is a blue solid that comes apart reversibly in the gas phase. It contains 36.84% nitrogen. What is the empirical formula of this oxide, okay? Well, also implicit in that statement, guys, is if the compound is 36.84% nitrogen, the kind of unspoken thing is that it is also 63.16% oxygen, okay? Now, to find the empirical formula of this compound, we're going to, again, make an assumption. I'm going to assume, because I like to assume round numbers, we're going to assume we have 100 grams of this substance that we are working with, okay? If we have 100 grams of the substance, that means we're going to have 36.84 grams of nitrogen, and we're going to have, by extension, 63.16 grams of oxygen. I now want to change both these numbers, or both these grams rather, into moles, okay? So 1 mole of nitrogen has a mass of approximately 14.01 grams. Okay, that's going to cancel out. And if we do the conversion, we get 2.63 moles of nitrogen. Okay, for the oxygen, if I change this into moles, 1 mole of oxygen has a mass of about 16.00 grams. Okay, the grams are going to cancel out. And we're going to get 3.95 moles of oxygen. Okay? Now, to find the empirical formula, guys, I need to find the ratio of nitrogen to oxygen, or vice versa. The question is now, what do I divide by? When we are finding the ratio, guys, you always want to divide by the smaller number of moles, okay? In this case, the smaller number of moles is that of nitrogen. So when I find my mole ratio, here's how I'm going to do it. I'm going to find the ratio of oxygen to nitrogen. We'll divide by the moles of nitrogen because this is the smaller number, okay? So here we go. 3.95 moles of oxygen divided by 2.63 moles of nitrogen is going to give me, if I do the division, 1.50 moles of oxygen to every 1 mole of nitrogen. Now, you might think from this ratio that the empirical formula might look like this. NO 1.5. But that's actually incorrect, okay? Because here's the thing. When we make an empirical formula, you can't have a fractional subscript. It always has to be a whole number. Now, the easiest way to change 1.5 into a whole number is just to multiply this whole turkey by 2. And if we do that, it's going to be N2O3. And there we go. That's the molecular formula of this compound, okay? Now, if I was going to ask you guys to name this baby, could you do that? Hopefully you could. The name, if this was the molecular, say for the sake of argument that this was also the molecular formula of the compound, we would name that baby dinitrogen trioxide. And there we go. Okay? So, using these two examples, guys, hopefully that makes it easier to do your empirical and molecular formula stuff. Again, if you have questions on this topic, you can email me, but try to use this podcast as your example. And, if all else fails, you can also come during the question day and ask me questions in person. One more problem, guys. This one's a general stoichiometry problem. Okay, this is problem number 71 out of your book. And the question is, what mass of lead-2 sulfide, which is known as galena. This is a mineral. It has kind of a silvery, well, not really silvery, it's kind of bronzy colored appearance. is required to produce 2 kilograms of lead, okay? Galena is an ore of lead, and as you guys probably know, most free metals are refined from some mineral, some chemical compound where we have to isolate the free metal from that, okay? So we're going to do a stoichiometry problem here and figure out, well, how much of this substance, lead-2 sulfide, do I need to make 2 kilograms here of lead, okay? Well, one thing we need to do first in order to solve this problem is we need to know what the formula of lead-2 sulfide is, okay? Now, if you go back to our list of ions, we know that a sulfide ion is an S2-, a lead-2 ion would be Pb2+, therefore lead-2 sulfide would have the formula of simply Pbs, okay? All right, now here's how we would do this problem. It's kind of a throwback, again, to last year. This is a stoichiometry problem. When we do a stoichiometry problem, guys, we're always going to start with the given. So our given information, guys, is we have 2 kilograms of lead. We're going to figure out at the end what mass of lead sulfide we would need to get 2 kilograms of lead if we're going to refine it somehow. So let's start with this given information. And in fact, I don't like using kilograms. I'm going to change that to grams right away. 2 kilograms, the same thing as saying I've got 2,000 grams of lead. That's what I'm looking for at the end of my chemical process, okay? Now, I can't go directly from grams of lead to, at the end, grams of lead sulfide, which is what I want to find. The first thing I'm going to need to do, guys, is I'm going to have to change this lead, okay, into moles. If I look at my periodic table, 1 mole of lead has a mass of, I think, if my memory serves me correctly, 207.2 grams. There we go. Now my grams of lead is going to cancel out. I'm going to be left with moles, okay? So there we go. Now the next thing I want to do, okay, is at the end of the day, I want to know the mass of lead sulfide that would be required to make 2 kilograms of lead. If I look here at my compound, okay, lead sulfide, this is my ore of lead, I can see that in every 1 mole of lead sulfide, there's 1 mole of lead, okay, just from the formula. So I'm going to multiply here again by a ratio, which tells me that there's 1 mole of lead sulfide for every 1 mole of lead, which has the element symbol Pb, okay, that I get out at the end of my chemical refinement, okay? So moles of lead goes away, and lastly, and I'm going to have now units of moles of lead sulfide. The last step now is I can change moles of lead sulfide into grams of lead sulfide, and so here we go. If I do that, the molar mass of lead sulfide that I can get by adding the molar mass of lead to the molar mass of sulfur is going to be 239.26 grams in every 1 mole of lead sulfide, PBS. There we go. That's going to cancel out. Okay. If we go through now, guys, and do the math by dimensional analysis, I'm going to find that in order to get 2 kilograms of lead out, I would require at least 2,309.46 grams of lead sulfide. That would be my answer. But of course, when we talk about significant figures, you're going to learn that we wouldn't actually carry through that many numbers. We would actually probably round this to 2.31 times 10 to the 3rd power grams of lead sulfide would be required. But more on that in another podcast. Anyhow, guys, here you go. There's a tutorial on some of the tougher problem types out of Chapter 3. I hope that was helpful. If you guys have questions on any of the material, feel free to email me. But I remember that I am going to be leaving on Wednesday, the 15th of June, and I will not be back until the beginning of July. So I hope you guys are enjoying yourselves. I will see you in August. Look out for the next podcast, which is going to be on significant figures, accuracy, and precision, based on the reading you guys are going to have out of the book. Goodbye. Have a good summer.